Today, we're going to continue looking at patterns of repeated addition. And we started yesterday calling them linear functions. This brought up a lot of memories. So once I said repeated addition, we should start thinking multiplication. We got to look for where the multiplication is happening here. And once I said linear functions, we should start thinking y equals mx plus b. It's backwards from the way that I like to think about it, but that might be the way that's the most common way we encounter linear functions. Y equals mx plus b. We want to identify m as the slope. Makes sense because m does not, it does not appear in the word slope. Well, I'm sure it makes sense in some language. So m is the slope, and the slope is the ratio of the rise to the run. It's how y is changing divided by how x is changing. And b is the y-intercept. So that means that the point 0b is on this graph. There are a lot of ways to think about linear functions, but this is the most common one that we may have encountered at this point in our mathematical lives. We've been trying to break down these patterns of repeated addition and relating it to our whatever pre-existing ideas we have of linear functions and slope and y-intercept, and whatever pre-existing notions we have about multiplication being repeated addition, the way that I like to think about multiplication in my algebra class. To that end, we've been looking at these linear functions in multiple different ways. We started off by looking at a table of values. Then we also talked about writing a sentence describing what's going on. The other thing that we wanted to start describing our linear functions with is an equation. And the one that hasn't entered the picture yet, the space down here, is the graph. So here are 4 ways that we can represent linear functions. These are 4 ways that we can represent a lot of things in math. And we want to understand how they're all related. From a table, we want to be able to come up with a sentence, or maybe an equation, or a graph. If we're looking at a sentence, we want to think about what that means in a table, what that means in an equation, how that would appear in a graph. If we're given an equation, we would want to think about how the equation can be described with a sentence, or how the equation would create numbers in a table, or how the equation can produce a graph. And then, although we haven't talked about graph, you can see where all the connections we're going to want to make are. Looking at a graph, how does the graph show up in the table? How does the graph be described? How could we describe the graph with a sentence? And how could we describe the graph with an equation? We have 4 descriptions of linear functions, and we want to understand how they're all related. Here are 4 descriptions of linear functions we want to understand how they're all related. And then for a more abstract goal, we also want to understand the process by which we understand how they're all related, so we can extrapolate this to other types of operations. Specifically, we're going to switch from repeated addition to repeated multiplication and describe our patterns of repeated multiplication with exponents, because exponents are repeated multiplication. So let's take a look at an example and think about what's going on. I'm going to start by writing an equation, and we're going to create a table of values for that equation, and then we're going to create a sentence for that equation. So let's say that y is equal to, and I'm going to write it in the way that I like to write it. I'm going to say y is equal to 23 minus 4x. So I want to use this to build a table, and I want to use the table to write a sentence. And then I want to use the sentence to go back to the equation and see how the equation is actually that sentence written in mathematical terms. So, algebraic terms, I don't know. Is everything in mathematical terms that we're doing right now? So let's look at a table of values. I'm going to leave a couple spaces. I'm going to say when x is 0, y is 23. So that's a point that we can come up with right away. Maybe we recognize that because 23 is the constant term, and the constant term is the y-intercept, and the y-intercept happens at 0, comma b. Or we can notice that if we plug in 0 into the equation, we get y is equal to 23 minus 4 times 0, or just 23. So a lot of ways that we can come up with that. So we're thinking of starting at y equals 23. Or we could say if x equals 0, y is equal to 23 minus 4 times 0, or 23. We could just get more points in the table by plugging in values of x. So let's plug in 1. If x is equal to 1, I get y is equal to 23 minus 4 times 1. 23 minus 4 is 19. That took longer than I expected it to. Me subtracting 23 minus 4. Let's plug in 2. If x is equal to 2, we get y is equal to 23 minus 4 times 2. 2 fours is 8, and 23 minus 8 is 15. All we're doing is simplifying things with the order of operations. And if I plug in x equals 3, I'm going to leave a space for stuff. Y is equal to 23 minus 4 times 3. 23 minus 12 is 11. So when x is 3, y is equal to 11. What we want to notice is where the minus 4 shows up in the y's. The minus 4 is telling us how y is changing. Notice that from 23 to 19, we subtracted 4 one time. From 19 to 15, we subtracted 4 again. But from 23, we subtracted 4 two times. And then from 15 to 11, we subtract 4 again. But from 23, we subtracted 4 three times. I'm going to go full Burns. Thrice. Because that's a word that needs to come back. 3 times, or thrice. Now we can see how the pattern works, where that negative 4 shows up. And now we can do the negative 4 in the numbers that we don't normally count with. So if I just plug in negative 1, then I get y equals 23 minus 4 times negative 1, or 23 plus 4, which is 27. So we're subtracting 4 negative 1 times. And here's that negative 4 showing up again right from the equation. And if x is equal to negative 2, we should see a negative 4 show up again. We must be at 31. And here's the negative 4 showing up. This is the last one I get to write, so I'm going to use a fantastic 4. These are all points that we can find by just plugging in values. But we want to go past just plugging in values like some machine. And we want to see the relationship between how the y values are changing in the table and where those changes are coming from. So what we're reading this as is 20. We start off at 23 and subtract 4 a bunch of times, and the x represents a bunch of times. So this equation is start off at 23. So y specifically starts at 23, and then we subtract 4. And then the times x is a bunch of times. Or we could say that as every step, like we were doing it yesterday. Or since the size of each step is 1 unit, we could say every 1 unit. So any questions? What we want to do today is mess with the step size. So today we want to mess with the step size. So let's change. Notice that in this, let's write a sentence for this particular equation. We're starting off at 23 and we're subtracting 4 a bunch of times, or every step. And every step is 1 unit. So each step is 1 unit long. So our sentence describing what's going on, we would say y is equal to 23 when x equals 0. That's how we describe where things start. Then we describe what's happening, and we'll say, and y is decreasing by 4 every 1 unit. Y is 23 when x is 0. Here's where we are deciding where things start. Then we're saying what's happening to the y, and we're saying how often that happens. Where y starts is going to be any fixed point, which includes, usually, if we're all about the y equals mx plus b, the y-intercept. So where y starts could be any fixed point like the y-intercept. I don't know why I said fixed. Any point like the y-intercept. Then we notice that y is decreasing by 4. This is a description of how y is changing, what's happening to y. Decreasing by 4, which means subtracting 4. And then finally, this every 1 unit is the step size, or how often that happens. So we've got this starting, which we could think of as the y-intercept. We've got what's happening to y and how often that happens. We've got some change in y. And then how often that happens is some change in x. So all we're doing is taking our familiar concept of slope is equal to rise over run and just describing what's going on. What's happening to the y is the change in the y, which we usually call the rise. And how often that happens is the change in x, which we usually call the run. And our practice is to combine the rise and the run into one number called the slope, because we can with a linear function. Looking into the future, it works out for a linear function because multiplication and addition are right next to each other. Multiplication is just repeated addition, and the change in x is addition. Let's look at another example. I'm going to still start at 23. I'm going to still decrease by 4, but instead of doing this every 1 unit, I'm going to do it every different number of units. And we're going to think about how that's going to affect the table and how that's going to affect the equation. So leave a space for an extra line in the table above the x's. I'm going to still start off at 0 and 23. Y is still going to decrease by 4. But I'm going to change the step size. Instead of each decrease by 4, so mark that out. So we're still decreasing by 4 each step. Still decreasing by 4 each step, but I'm going to change the step size to 5. So this is not happening every 1 unit. This is happening every 5 units. Should have been 3. Oh well. So now each step is going to be 5 units. We're still subtracting 4 at each step. Step is a little bit of a fishy word. We're still subtracting 4 each step, but now each step is 5 units. So the line that I want to insert above the table is the number of steps. And I want 0 to be 0 steps. Each step is 5 units. So when x is equal to 5, that's 1 step. When x is equal to 10, that's 2 steps. When x is equal to 15, that's 3 steps. And so when x is equal to -5, that's -1 step. Weird to count with negative numbers, but totally doable. We want to be able to describe what's going on with a sentence. So we'll still say that y is equal to 23 when x equals 0. That's any point as a starting value, a place to start. And we'll say that y is still decreasing by 4. Y is decreasing by 4. But now instead of this happening every 1 unit, we'll say this happens every 5 units. So when we see that the y is decreasing by 4, every 5 units. The decreasing by 4 is the change in y, which we usually call the rise. So we could use this to say that the rise is -4. How often that happens, we can write as the run. And we like to combine the rise and the run into one number called the slope, which we abbreviate with m. The slope is the ratio of the rise to the run. We usually just say slope is rise over run. So in this case, the slope is a rise of -4/5. Now we can see what the equation should look like. So we're going to write y equals b plus mx. So let's say y. So to encode this equation, this sentence into an equation, this sentence is a description of what's going on in the table. And so now I want an equation that describes what's going on in the table. I want this equation to describe this sentence. So we'll say y is equal to, where we start is 23. What's happening to the y is we're decreasing by 4 every 5 units. That's why our slope is -4/5. And so we're going to subtract 4/5 a bunch of times. Since we're doing a repeated addition, we use multiplication and x to indicate the number of times that we're doing this. So we got the table, we've got a sentence. From the sentence, we can write a slope. From the sentence, we can also write an equation. 3 different descriptions of what's going on in this function. Any questions? I want to play with this step size idea for a moment, because when you look at the equation says something maybe slightly different. We might interpret this equation as saying y equals 23 when x equals 0. That doesn't change. But we might be describing the change as decreasing by 4/5 every 1 unit. So we might also, what we want to notice is that slope is a ratio. So slope is proportional. So decreasing by 4/5 is also decreasing by 8/10. So slope is proportional. Slope is a ratio. So -4/5 is also -8/10, is also -12/15, is also positive 4 over -5. That would look weird. So let's write negative, I'll just go one more, 16 over 20. So -8/10 would be decreasing by 8 every 10 units. And that's exactly what happens. 23 minus 8 is 15, and 0 plus 10 is 10. So slope is a ratio but we can also interpret the slope as the ratio of -4/5 to 1. That would be weird of us to do, but that's what we've written in this equation. We've written the slope as -4/5, so we're reading this as a ratio of a -4/5 to 1. If we start thinking of a step size as being 1, instead of subtracting 4 every 5 steps, we're going to subtract 4/5 every 1 step. So reading this, ignoring that table, ignoring this sentence, and just going with the slope of negative 4/5, we might write y equals 23 when x equals 0. But we might write a different set of changes. We'll say something like y is decreasing by 4/5 every 1 unit. Now, if I'm going to make a table of values, I'm still going to start off at 0.23. But instead of decreasing by 4 every 5 units, I'm going to decrease by 4/5 every 1 unit. So 23 minus 4/5 is going to be 22 and 1/5. And now I'm going to remember why I wanted to make each step size 3 and not 5. I'm going to subtract 4/5 again for when x is equal to 2. So I'm just making one size, step sizes of 1. So 22 and 1/5, if I subtract 4/5, I'll have 21 and 2/5. Subtract 1/5 down to 22, and then subtract 3 more fifths to 21 and 2/5. And then I'll take another step. Once again, I'm taking step sizes of 1. And I'm going to subtract 4/5 again. So 2/5 drops us down to 21. So 21 minus 2 more fifths will be 20 and 3/5. And then I'll take another step. And subtract another 4/5. So 20 and 3/5. If I subtract 3/5, that'll get us down to 20. And I need to subtract 1 more fifth. So I'll be at 19 and 4/5. And then if I take 1 more step with a step size of 1, I'll subtract another 4/5. 19 and 4/5 minus 4/5 is going to bring us to 19. This is the same place that we were in our original function. Subtracting 4 every 5 units is the same as subtracting 4/5 every 1 unit. This is why we like linear functions so much. This is exactly how we would think. This is our default mode of thinking. The default mode of thinking is to think linearly. If we're bargaining on the price of an object and I say, I offer $20, and you say, how about 30? We split the difference, which is us thinking linearly and drawing a line between our two offers. And we split the difference and come up to 25. Because we're thinking of drawing a line between those two, and we're splitting the difference in an adding and subtracting way. Any questions? Is usually when people start to rebel because everything's in fractions. So, and I sometimes wonder whether I should be doing this problem in mixed numbers or if I should just do the problem in improper fractions so that we could just subtract 4 a bunch of times. So 23 over 1, if I do 23 times 5, I get what, 115? Is that right? 115 over 5. I don't know why I'm wondering. I know I'm bad at arithmetic, and I have a calculator right next to me. So I could be like all 23 times 5. It's 115. I did it right. And if I subtract 4/5, 115 minus 4 is 111 over 5. And then minus 4 again is 107 over 5. And then minus 4 again is 103 over 5. Minus 4 again is 99 over 5. And minus 4 again is 95 over 5. And these are all those mixed numbers. So if I do 22 and 1/5, and I make that a fraction, that's 111 over 5. 21 and 2/5 as a fraction is 107 over 5, and so on. At least when I use 5s, the decimals work out. Because we're subtracting 0.8 each time. So 23, and then we get 22.2, and then 21.4, and then 20.6, and 19.8, and then 19. Because 4/5 is 0.8. Maybe this is why I chose 5, so everything's like a nice 0.2, so I could go this far. Because if I was using 1/3, then the decimal is a 0.3 repeating, and all of a sudden I can't just, that's just too much to write, I guess. Any questions? All right. Tomorrow, we're going to look at why I added this extra row of steps above the 0, 5, 10, 15. Why did I want to include the number of steps, 0, 1, 2, 3? So tomorrow, we'll probably take a look at this example yet again and consider the step size and where the multiplication comes into things. Because I'm less concerned with you being able to grind out 1,000 problems where I just give you 2 points and you find the equation of a line, and more concerned with how you view linear functions and how we think about linear functions. That way, when you encounter functions in the wild, you'll know what to look for rather than just randomly try to make a line fit to what you encounter. There needs to be a reason that you pick a linear function, and it should be a better reason than that's the one that I know. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.